All right, so in trig, the trig you're used to has right triangles in it. In fact, only right triangles would work. So let's go through some of the stuff you may remember. You may or may not remember this, but the variable that we usually use for an angle is theta, and it looks kind of like that. Draw me a right triangle. It's got a theta right there. All right, and now if this right triangle had lengths on it, let's say I said it was a 3, 4, 5 right triangle. Actually, then that west side wouldn't be 3. This would be like 3, this would be like 4, and this would be like 5. Does that ring a bell? That's called a Pythagorean triple, because those three numbers work nice for the Pythagorean theorem. Because why? Because 3 squared plus 4 squared is equal to 5 squared. And there's not too many combos that work out so nicely. You know, 3, 4, 5 is one of them. And of course you could double them and say 8 and 6 and 10. But there's another Pythagorean triple that's really common you should know. 5, 12, 13. Very good. So if you draw another really skinny one, and make it 5 on this side, 12 on this side, and 13 on that side. Why would you need to know that, you say? Well, I can tell you one thing. It's on the ACT tests list of things that they can test you on. How many of you have already had the ACT? All right. Now, you had one version of the ACT. When you take it again, are the same exact questions going to be on there? No. They sometimes throw on this, sometimes they don't. But Pythagorean triples are good to know. All right. So then let's talk about sine, cosine, and tangent. If you had this triangle, you would, for instance, do sine of some angle, and typically, well, on this one, this actually is some weird answer, like 22.8 degrees or whatever. So, but I'm just going to say sine of 30 degrees, and then you'd have an angle. All right. So let's say I didn't know how long the sides were, but let's say I knew this was 30 degrees. Then how would I set this up? Well, I'd have to know one of the sides to be able to make this work. Let's say that I knew sine of 30 degrees was equal to, sine is opposite over hypotenuse. Do you remember that? If you don't remember that, SOHCAHTOA should be on your list to memorize tonight. Sine is opposite over hypotenuse. Get where I'm going here? Opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. How many of you remember that? That's most of you. If you didn't know that, to be honest, you're way behind, because that's the baby trig that you're supposed to already know. We're moving on to the big time trig now. Okay, so anyway, go memorize SOHCAHTOA tonight if you haven't already got it memorized. All right, sine means opposite over hypotenuse, like it says right there. And this opposite side, let's say I don't know what it is. I'm going to call it x. And the hypotenuse side, let's say I knew it was an 8. Then I could answer this question and figure out what x is. This is just simple, basic right triangle trig. So sine of 30 would be x over 8. Wouldn't this be easy if I just knew what sine of 30 was? Because then it would just be like, you know, 0.93 is equal to x over 8. And then that'd be easy to solve, wouldn't it? Well, you can use a calculator to figure out sine of 30. So grab your calculator. Type in sine of 30. Hit enter. And I guarantee you we're going to get two different answers. Some kids are going to get one answer, and other kids are going to get another answer, and that'll be a good learning moment. Okay, have you typed in sine of 30? What'd you get? Oh, wait a minute. I'm hearing some people say one thing and some people say something else. See what I'm saying? Okay, why is that? How is that possible? Because you could be in radians or you could be in degrees. Everybody hit the mode button on your calculator. And look, are you in radians or are you in degrees? How many of you were actually in radians? So you were doing it with, you weren't doing sine of 30 degrees, you were doing sine of 30 radians. Switch your calculator to degree mode, because we're going to pretty much be in degree mode all year. Next year when you go to calc, you'll be all grown up and you'll be able to move into radian mode all the time. But for right now, we're used to degrees more. So everybody get your calculator into degree mode and now try it. Sine of 30, and what do you get now? 0.5. Okay, so what did we just figure out? We figured out sine of 30 is 0.5. So that right there is 0.5. 0.5 is equal to x over 8. Isn't that a simple little equation? And I hope your last semester teacher told you how to clear a fraction out. You'd multiply both sides by 8 to fix this denominator issue here. So we'd multiply this by 8, and a half times 8, I can do that in my head. That's half of 8. 4. So I just figured out that 4 equals x, or x must equal 4. Does that make sense to you? That's like simple trig. And I know I went really fast, but that's the kind of trig problems you've done before. Do you remember that Your teacher probably hammered on this, that this only works in right triangles. You can't go beyond 90 degrees. Do you remember that? Okay. Now what we teach you how to do in this kind of trig, to be able to handle all these real world applications of trigs, rotation, vibration, sound waves, light rays, orbits, vibrating strings, like, you know, when you pluck a guitar string, pendulum swinging back and forth, all these kind of things. To get a little more advanced in trig, we need to be able to go beyond 90 degrees. So, just for a moment, we just did sine of 30 degrees a second ago. And it came out to 1/2. What if I told you there's an infinite number of things where you do sine of it and it comes out to 1/2? There is. Here's why. The sine graph, if I graphed sine looks like this. It's a wave. It goes back and forth and back and forth. Do you see how it's going to keep hitting over and over and over? It's going to have an answer over and over and over again. So sine of 30 degrees is actually, like right about here is 30 degrees. And it hits at 1/2. What's the highest sine ever goes to? Do you know? It goes to 1. All right, so if it hits here, it's going to hit here, it's going to hit here, here, here. It has an infinite number of things that will equal 1/2. All right, so that's one thing to kind of stretch your mind on, is that since sine is a wave, there's lots of things that'll make 1/2. There's not just one answer. A lot of times in this, there's 2 or 3 answers, or even 4 answers. When we get to the end of trig, some of our problems will have 6 answers for them. All right, so let's talk about what's another thing that would have sine of something else that would equal 1/2. All right, I want to just make you think about this for a second. If this, let me actually go on into my presentation just a little further. There's some terminology you're going to have to know. And how much you write down in your notes kind of determines how well you are probably going to do in this class. Not because writing it down makes you a genius, because writing it down helps you remember it. It does. It also gives you something to look back on. So if you are the dedicated type of student, you might actually look back on your notes and a few days from now be able to use this. For those of you that I know I'm not going to do that, there's no way. At least write it down, because there's more of a chance you'll remember it when you need it. All right? There's a few things you need to know. I'm not going to make you write this one down, the word angle. I know you know what an angle looks like, but do you know that an angle is determined by rotating a ray around its end point? All right, well, watch. This is a ray. You see how I'm rotating it around? The angle that's important here is the angle between the base here, which is called the initial, and this side, wherever I stop. If your heart stops beating, you're called terminal. This is where this angle stops. That's called the terminal position for it. It's where it stops. So there's the initial position down here and the terminal position wherever it stops. Would you agree if I stop right there, I got a 90-degree angle? How about if I go a little further? I'm past 90, right? See this circle here? What if I go all the way around it? How many is that? Then this whole thing that's open here is a 360-degree angle then. All right? How about this? This was 90. How much is this? 180. How much is that about? Good guess. If this right there is about 30 degrees, then how far is the open part? Well, if it adds up to a total of 180, it has to be 150. All right, so now here's my question. Would you please use your calculator and use what I just wrote on the board and figure out something else where you do the sine of it and it comes out to 1/2. Do the sine of something else, not sine of 30. Do the sine of something else. Oh, it wasn't too hard. There's only 2 numbers in the board. But you got it before everybody else. What'd you do? Sine of 150. Sine of 150 is also 1/2. Well, that's because 150 and 30 go together. Do you get how the 30 and the 150 go together? They're parts of 180, yeah. So let's use that a little further and say, what if I had started with sine of 20? Everybody type in sine of 20. What's the sine of 20 degrees? 0.368, blah, blah, blah. Okay. Make me a prediction. What's the other angle? That's going to, sine of that's going to equal the same thing. Try 160. Try sine of 160. See if you get the exact same thing. You catching on to the pattern here? Okay. So what we just drew right here is the main thing you have for homework today, which is to learn how to draw a reference a reference triangle. This is not a triangle that has a 150-degree angle, and it isn't. But it still works to figure out the sine of 150, doesn't it? Because I just used the 30 instead. All right, so you're going to learn how to draw a reference triangle like that. So let's say I had given you the angle 60 degrees. You'd be able to say, okay, well, normal starts here, and then 60 degree was end about there, right? So then I can make a triangle for that. That's easy. It goes like this. That's 60 degrees. That's called a reference triangle. Everybody draw the reference triangle for a 60-degree angle, just like I just did. Now see if any of you can draw the reference triangle if it was a 100-degree angle. Let's take a shot at it. That's the reference triangle for a 60. What would 100 look like? I'm going to move this guy over. Well, hopefully you knew where 100 was at least. 100 goes from here to about there. It's just more than 90, right? But where to make the triangle? You don't do this. You know why? Because then you have a angle that's bigger than 90 again. And we got to go back to having a right triangle that doesn't have big angles in it. So where am I going to go? Down. That is the reference triangle that goes with the 100-degree angle. Because this part's the 100. How big is this part? 80. So if you didn't want to type in sine of 100, what could you type in? Sine of 80. They give you the same answer. All right, that's called the reference triangle. And you're going to have to draw reference triangles like 35 times today. So if you don't understand it, ask me. I'm going to give you... So if you had a 90-degree angle, you would draw your reference. You would actually not be able to draw a reference triangle for those. We're not going to mess with your head today on those. That's because in theory you have a 0-degree angle in your reference triangle, but that's going to mess with your head, so we're not going to do that. All right, so see if you can handle this. What's bigger than 180, like maybe 200? Draw me a reference triangle that would work for a 200-degree angle. First, you got to figure out where the 200 would pop out. Get used to drawing something like this. A circle with the big axis, X and Y axis going through it like this. You're going to draw this so many times in the next month? Seriously. Over and over and over and over again. We draw so many circles to try to figure out trig questions. All right. So where's 200? Well, if this was if from here to here would have been 180, we're not going to do 180. We're going to go bigger. We're going to go to, say, 200. I hope you know just intuitively where that triangle is, but if you don't, it's like this, and then you have two choices. I bet some of you went this way, and that's not right. You need to go this way. Why? Your triangles will always go back and touch the x-axis. Your triangles need to always go back and touch the x-axis. All right, so if that was 200, that means this is 200. What's the little angle on the inside of my reference triangle? This angle is 20. Very good. Does that make sense to you? So then, if that's 20, And these all have to add up to 180. Good fact to know for the ACT. These have to add up to 180. And this one's 90 because that's the whole point is we're making a right triangle. 90 plus 20 means we've already used up 110 degrees. So how much is this other one? 70. Yay. You're learning to make reference triangles. Now some of you might be going, well, wait a minute. When I do sine of 20, I get a different answer than when I do sine of 200. And it's the exact same thing, only negative. Let me show you why. Do you get how sine goes back and forth and back and forth? It goes into the negatives, doesn't it? So sometimes your answers are negative and sometimes they're positive when you have sine. Because it goes from all the way up to 1 to all the way down to negative 1. So your answers for sine are somewhere in between positive 1 or negative 1. So sometimes your answers are negative. That's 180 right there. So when I went past 180, it got negative. All right, you don't have to understand all of that. What you have to understand is that when you draw the reference triangle, sometimes the answers aren't exactly the same. Sometimes they're negatives of what you had before. Okay, now the next part. I need to help you understand the difference between a degree and a radian. All right, if I was to label this thing in degrees, I hope you would get that a triangle that doesn't open up at all would have 0 degrees. Does that make sense to you? If it didn't open at all, the angle never swung up and swung up to like here. If it never opened, it would have a 0 degree. This would be like a 30 degree. This would be like a 60 degree. This would be like a 90 degree. Do I really have to keep labeling all the way around? You probably can handle the rest of them, right? And then it's going to get 180 here, and it's going to, what's this bottom one? It's kind of important. 270. Okay. Those are the easy kind because you get them naturally. You're used to them. Okay, but what you're not used to is radians. And a lot of trig is in radians. So we're going to draw. Everybody start with a fresh new circle. And I want to show you what a radian is, first of all. A radian's about 59 degrees. Why on earth did they pick exact 59 degrees? Seems crazy. You'll see why in a minute, because it's based on pi. But for right now, what you need to know is it's about 60 degrees, but not quite. So a radian, make an angle that's about like 60 degrees-ish. Okay? Do you know what happens at that magical place? This distance, let's say it's a radius of 8, is the same as this distance, which is a radius of 8, and that would have happened no matter what. Take a wild guess how long the arc is along the outside. If this is 8 and this is 8, how long is that, do you think? It's 8. It's when you draw in a circle, when you draw a wedge like this, where the radius is 8 and the other radius is 8, it isn't just with 8, it's with any number you want it to be. This number, as soon as you make the arc length the same exact thing, if you make it 8, that curved line there, then you've made exactly 1 radian, which is about 60 degrees-ish. That's 1 radian. Now, radians are kind of weird. They don't have units. I call them radians, but we don't have a unit for it. Whereas degrees, if I said 180, it doesn't mean 180 degrees until I say this. But radians, they don't have any units. I can give you a long, complicated lesson that would take the whole rest of the hour to explain why. Not going to. Just going to say that radians don't have units for now. Okay? They're radians, but we don't have a symbol for it. There's no little thing for radians. All right. Next thing. Radians are all based on pi. And let me give you the first one. Make a new circle. This is 0 radians, surprisingly. Makes sense, right? This is pi over 2, or half pi radians. Pi over 2 is in the exact same spot as what degrees would have been? 90. Good. 180 is pi. Because if this is half a pi, all the way to here should be 1 whole pi, right? That's pi. That's pi radians. What's pi really? 3.14, so that spot is 3.14, blah, 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 radians. It's about 3 radians. Remember how radians are about 60 degrees? It's just a little bit more than 3 radians. It's 3.14 radians. It's pi radians. So spots you have to memorize now. You don't just have to memorize 90 and 180 and 270. That was too easy. You could have done that in 7th grade. Now you have to memorize that that's pi over 2. That's pi. Somebody do this one? Not 2 pi. That's 1.5 pi. How do you do that?
1 pi.
3 pi, but then over 2. Very good. And then if you get all the way around, 2 pi. Can 2 pi and 0 be in the same spot? Yup. Why can it keep going? Because tangent and sine and cosine and all those things graph, they can just keep going. They can go forever. You can keep graphing it forever to the right. So I have to have bigger and bigger numbers. It's going to just keep on going and going and going and going. So we have to be able to keep going around the circle. In fact, if you wanted to go to where 3 pi would be, you just keep on going. You go all the way around to 1 pi, 1.5 pi, 2 pi. Where's 3 pi? 3 pi is in the same spot as pi is. And you just keep going. Where's 4 pi? 4 pi is the same as 2 pi. 5 pi? You get what I'm doing? Picking up what I'm laying down? All right, right there. Okay, so where's 1/3 of a pi? How about this? There's 0, there's pi. Where's 1/3 of the way there? Like right there-ish? Is that what you were thinking? All right. You're right. That's called pi over 3. Where's 2/3 of the way there? Can you do that with your head, in your mind? 2/3 of the way is like something like that? Is that about 2/3 of the way there? So that's 2/3 of pi. Sometimes we call it 2 pi over 3. For those of you that are like, oh, I can't take this anymore, you have to. We got more that we have to memorize. You have to memorize the thirds. You have to memorize the fourths, too. Yep. There's a lot to know. 1/3 pi, 2/3 pi. Would you agree that's the same as 3/3 pi? Right? 3/3 pi? Yes, it goes further. That's 4/3 pi. I would recommend you write this down. Stop talking, please. Thank you. Keep copying these. Get them all the way around to the finished position. This was 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. You get how you just have to count them up like that? This one's 5/3 pi, or 5 pi over 3. And then if I hit all the way, it's 6/3 pi. Isn't that the same exact thing as 2 pi? Yeah, it's just a different way to count to get there. Yes? We haven't done that one because it was, here, I'll do the 3 pi over 2 one. That was in the half pies. Let me just show you quick where that was again. That was 1/2 pi, 2/2 pi, which is the same as 1 pi, right? 3/2 pi was down there. All right, what haven't we done yet? We've done the 1/3, we've done the 1/2. What's left? The fourths. So draw yourself another circle. And if this is where pi is, always write that one down. It's a really, really handy one. If that one's pi, then you just have to figure out where it was 1/4 of the way there. 1/4 of the way there? It's like a 45-degree angle, isn't it? So surprisingly enough, 45 degrees is exactly equal to 1/4 pi, or pi over 4. I like to say 1/4 pi because that makes me think of the next one, which is going to be 2/4 pi, which would be right here. 2/4 is the exact same thing as half of a pi, right? What I said before. 3/4 pi is over here. This one, of course, is 4/4 pi. If you want to say it's 4/4 pi, it's fine. The 4's will cancel, but 4/4 pi. What's the next one? 5/4 pi. What's the next one? 6/4. What does that reduce to? 3/2. 3 pi over 2. Same exact thing, right? A 6/4. It's just a different way to count. I'm counting by fourths now. 6/4, and then the next one, 7/4 pi, and then the big finish, what's the last one when you get to there? 8/4 pi, which is equal to 2 pi, just like you want it to be, because it makes sense, because that's where we said 2 pi was in the first place. All right, so let's get that worksheet out to you so you can see what we want you to practice for today. Now, today shouldn't be too bad, but you don't want to get lost in this unit. If you get lost and you get 3 days behind, really hard to save yourself. You get 1 day behind, no big deal. Come in and get some help. But look at the keys, people. They're there for a reason. I strongly recommend you go and look at the key tonight. If you are lost, look at the key. Don't let yourself get far behind. This is the hardest unit in pre-calc. And pre-calc used to be considered the hardest class at the high school. It was the most dropped class at the high school. That tells you something. I think most people are saying that AP Calc is harder than this class. But it's like if you can make it through this class, then it's not that bad kind of thing. But this class is not easy. And why? Because of this unit. So don't underestimate this. You can do it, but you do not want to get behind. All right, that's all I got for the video for today. All right, I'm going to pause it for now and see if I need more. Okay, I am going to record again here and have a few examples off the worksheet. Number 1, the directions say for each angle, draw the terminal side. That just means where you start. In the correct terminal side of the angle, the terminal side is not where you start, it's where you end the angle. In the correct quadrant, and draw the reference triangle and label the reference angle. Okay, so I'm going to first of all figure out where on earth is 2/3 pi. Well, if this is where pi is, I hope you know the 1/3 pi would have been there. It's not there. 2/3 pi is like right about there. And you're supposed to label that spot as 2/3 pi. 2/3 pi. Am I done yet? No, I haven't drawn a triangle. The reference triangle, remember how I always said it has to go touch the which axis? The x-axis. So I'm going to go down, touch the x-axis. Hey, got a triangle. And now what's the important angle? The interior angle, the inside one, this guy. Put a little theta right there. And now here's the important part. It says to label the reference angle. That angle right there is not 2/3 pi. Remember when it was in degrees, it was easier. This was like 150 and this was like 30. Well, now this is 2/3 pi, so what's that? Very good. So theta, just go a little, don't try to squeeze it in there, it'll be too hard to get in there. Just put like a little arrow to it and say that must be 1/3 pi. Totally okay to say pi over 3, but 1/3 pi I think kind of will make more sense to you over time. Because this one's 2/3 pi, then this one will be 1/3 pi. Okay, I've labeled a reference triangle. That's it. That's all there is to it. Done with problem 1. Let's move on to problem 2. Take a second and see if you can figure out where 3/4 pi is all by yourself. See if you can draw the reference triangle and see if you can label the angle. That's the important one, the one on the inside. Okay, hopefully you said 3/4 pi was like about there. 3/4 of the way to here. And now I'm going to draw my triangle, drop down to the x-axis. I got a triangle. That's the important angle. Draw a little thing to it. It must be 1/4 of a pi. Raise your hand if you did that one right. Okay, awesome. Let's move on. I think you're getting the idea. How about something weird like 11/6 pi? Let's move to number 5. What? 11/6 pi? Well, it is ugly until you break it down and you realize it's really not that bad. It's just 1/6 pi over and over again. 1/6 pi plus another 1/6 pi plus another 1/6 pi. Okay, so let's figure this out. 11 pi over 6. That's 11/6 pi. So if I knew where 1/6 pi was, it's just 11 times that far. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. Did you get what I just did there? 6/6 is 1 whole pi, right? 6/6, I'm not done yet though, right? 7/6, 8/6, 9/6. Does that make sense to you? 10, 6, 11, 6. So I should now erase all those other lines except for that one, 11, 6. Do I have to have you have it in exactly the perfect spot? No. That's close enough. All right. So then, if that's 11, 6 pi, 11, I just labeled it wrong, sorry. 11, 6 pi, then how much is left? So that means this little triangle dropped to the x-axis, and that's the important angle, and that one must be what then? 1/6 pi. Very good. My reference angle is 1/6 pi. All right, good. I hope this feels easy to you. It is a little excessive, so why don't we skip a few? Why don't we say you can skip number 14. Go through and skip some with me. Cross off 14. Cross off, you know why I'm going to have you cross off 17? Look at 8/4 pi. Just think for a second. What is that? That's 2 pi. Cross off 17. Okay. Let's move on to skip 20, 23, and 26. And 29, 32, and 35. I don't know if you figure out a pattern out there, but anyway. Okay, let's do some that have degrees. Everybody look at number 19. Number 19 on your homework. Theta is 60 degrees. The last ones were just the ones down the middle. 23, 20, 26. Anyway, okay, moving on. We're doing number 19 now. 60 degrees. Where is that? Well, I know where that is. 60 is about here. All right, so if that's 60, that means this is 60. And have I got a reference triangle? Well, I got to just drop down to the x-axis. Boop, there we go. I've got my triangle. And it's already labeled. Boop, done with that. That's easy. That's all I have to do, isn't it? Well, that one just happens to have, if reference triangle is the normal triangle. You see what I mean? I didn't have to draw a second or a triangle over in that other quadrant. So now let's do a little harder one. Let's go to number, let's do 24. Number 24 is 315 degrees. Now, you remember before I kind of broke it down, and when it was 11/6, I figured out that was really 1/6 except over and over and over again. Well, 315, can somebody figure out that's really a whole bunch of whats? 45s. A bunch of 45s. In fact, if I had a calculator, which you do, I would take the 315 and divide it by common things, and eventually you'd figure out that, 315 is really a whole bunch of 45s. 315 divided by 45 comes out to 7 45-degree angles. Very good. So if you always start with one of these guys, and you figure out where is 45, okay, there's one. That's one 45-degree angle. 2, 3 45s, 4, 5, 6 45s, 7 45-degree angles. Yay, that's 315. If it's 315, can't you see how much is left until you get to 360? How much is left here? We've already gone 315 to get here. One last 45-degree angle, right? So that must be 45. So I've drawn a reference triangle, and I've got the reference angle. That central angle, the one on the inside, that's the important one. All right. Yes?
Number 27 is 180.
All right. What do you do for something like 180? Let's do that. Number 27. So when it says theta is 180, I hope you know where 180 is. You know where it is? All right, so it's right here. All you have to do is draw a line that goes over there, put a dot on the end, and label it just like you would normally label it 180, or in this case, you could have labeled it pi if we were in radians, but we're in degrees right now, so we're going to use 180. Can I make a triangle for that? No, it'll be a triangle that have a 0-degree angle in it, and you therefore can't make a triangle for that. So when you can't make a triangle, you can't make a triangle, and it's okay. You aren't expected to try to make up a triangle. Can you still do sine of 180 degrees? Yeah, you can. You just can't do it with a triangle. We'll teach you how to do those later. Those are a special thing called quadrangles. There's 4 of them like that. It won't make sense in the same way that other ones make sense in terms of like opposite over hypotenuse and stuff, but it'll make sense when it comes to, if you know sine is really doing this, guess where 180 is? Does that make more sense to you? This was 90 degrees. This was 180. If you said sine of 180 on the calculator, it would tell you the answer was 0. How could you have two things divided and have it equal 0? If one of the sides, the top one, the opposite over hypotenuse is what sine is, right? The opposite side is actually 0 in length. All right, don't let that blow your brain too much. Just know you can't make a triangle for the kind like 180, or if it said 360, you couldn't make a triangle. You couldn't make a triangle at 90. You couldn't make a triangle at 270. Negative, oh, negatives. Thank you for bringing that up. Where is the negative 60? Negative means down that way. Negative 60 would be like right there. It goes the opposite direction, yes. I'm sorry, I totally forgot to talk about negative angles. Yes? You go around again. Okay, so here's 360 all the way to here. So 400 will be 40 more degrees than that, and it would go like to there. So where was 60? 60 was like this. Where's negative 60?
It's on the other down.
So negative 60 would be down there. That would be 60.
So for the one that you did, the one all the way around, is it just still the same kind of approximate?
Yeah, if you asked me to draw a reference triangle for 400 degrees, I'd go, okay, 360s to here, 400 is another 40 degrees. So I'd say that my triangle goes like this, and this must be 40. Your reference triangles are normal triangles, and they'll never have negative angles in them. They'll have nice, normal little angles in them. If they ever don't have a normal angle, then they're like one of those special places. Like this can't have a triangle there. At 0 degrees, you can't make a triangle. At 180, you can't make a triangle. You'll have a 0 degree angle in it. So there's only 4 spots where you can't make triangles. These 4 spots. Every other spot, you can make a reference triangle. And it'll always be a nice little normal right triangle, and it'll have normal numbers in it. And it won't have negative numbers in it. Question? Okay, read it, number 3. Theta equals pi over 6. All right, 1/6 of the way to pi. Here's pi. Pi over 6 is 1/6 of the way there, so it's like not very far. That's 1/6, 2/6, 3/6 would be halfway, right? So that makes sense. So 1/6 pi is that spot right there. Take a guess how many degrees that is? It's 30. Pretty good. So if you use pi over 6 on your calculator, or you use 30 in degrees or pi over 6 in radians, you get the same answer. Okay, so anyway, what is this angle right there? You don't want to change it from radians to degrees. You want to stick it in radians. So that angle is pi over 6. You're getting used to a whole new language, so don't stress if the sum of this doesn't feel natural to you. You're learning to speak trig. All right, that's all the video I have for today.